Are you stuck at home and bored? Well, what better way of spending your time than to try to solve together the Schrodinger equation for the hydrogen atom? The Schrodinger equation is one of the most important equations in all of physics, and certainly is the foundational equation in quantum mechanics. However, it is not generally easy, if not impossible, to solve the Schrodinger equation for a system. There are only a couple of examples that can be solved analytically and yield a nice solution. Luckily, one of these examples is the electron in a hydrogen atom. Let's start with the basics. I will assume that you have a basic knowledge of quantum mechanics and ordinary differential equations. The Schrodinger differential equation is a partial differential equation that depends on time and space. The linear time dependence comes from the left partial derivatives. The space dependence comes from the h on the right. The h on the right is known as the Hamiltonian operator, which is a sum of the kinetic and potential energies. The kinetic energy is given as in classical mechanics as p squared over 2m. And the potential energy is given in terms of the potential that goes into the problem. Recall also from quantum mechanics that the linear momentum operator is defined in terms of the gradient. And the potential for our problem will be the electromagnetic Coulomb potential, which is given as an interaction between the proton and the electron separated by a distance r. When we put these two expressions into the Hamiltonian, we get the explicit expression for it in terms of the gradient squared, which is also known as the Laplacian. We'll say more about this later. Notice also that h bar, which is Planck's constant, is a tiny constant that has the units of energy times time. And h, as I just mentioned, is the total energy of the system. These two should hint at the fact that energy comes into play at some point. There are two other important principles of quantum mechanics. The first one says that the psi function, which is a solution to the Schrodinger equation, is a complex wave function. It is complex because it allows complex values, and it's a wave function because it's a wave solution of the Schrodinger equation. What's the interpretation of this wave function? Well, we know from quantum mechanics that the wave function squared represents the total probability of finding the particle somewhere in space. There's a principle known as the Born principle, which says that if you integrate the square of the wave function over all of space, that is equivalent to integrating the probability of finding the particle somewhere in space over all of space. Well, essentially that gives the total probability, and because the total probabilities add up to 100%, that gives us that the integral of the square of the wave function over all of space has to be equal to 1. Another way of saying this is that the wave function has to be normalized. How do we solve such an equation? From the theory of partial differential equations, we know that there's a standard method known as separation of variables method, in which the wave function is written as a product of functions of the individual variables. As a first step, we're going to separate the time part and the spatial part. Now notice that the spatial part is not a single variable function either, because it depends on 3 spatial variables, but we will not worry about it for now. If we take this expression and we plug it into the above equation, we get an expression of this sort. We can also factor out things because on the left, the phi is not affected by the time derivative, and on the right, the t function is not affected by the spatial derivatives. As a next step, we divide both sides by the product of t and phi, and we obtain the following equation. Now this is a crucial step. On the left, we have an equation that depends only on time. On the right, we have an equation that depends only on space. But the two are equal to each other. Because they're dependent on mutually exclusive variables, the only way for them to be equal to each other is if they're equal to a constant. And this constant we call capital E, and we associate it with the total energy of the electron. We can justify this choice in two ways. First of all, recall that h bar has units of joules times time. So h bar over T must have units of joules times time divided by time, which gives units of joules that are units of energy. And the other justification is that the Hamiltonian is the total energy of the system. We can now solve the time part of the equation. And notice that I've replaced the partial derivatives with just good old derivatives because the function now depends only on time. This is a first order ordinary differential equation which can be separated and integrated. Once we do this, we can get an expression for t, and if we exponentiate both sides, we get that t is just a phase times some constant. Now recall that the wave function has to be normalized, so we're going to set a equal to 1 for now, and this is equivalent to saying that we're, for now, absorbing the constant a into the spatial part, and we'll take care of the normalization later. This essentially says that we can write the psi wave function as the product of a spatial function phi times a time phase. This is very profound because it tells us that the square of the wave function at time t0 is equal to the square of the wave function at time t greater than 0, and they're both equal to just the absolute value squared of the spatial function. More importantly, because the phi function satisfies the equation h phi of r equals e phi of r, that tells us that phi of r is an eigenfunction of h in the language of quantum mechanics with eigenvalue e. This is known as a stationary state equation, and the reason why it's known as a stationary state equation is because the partial derivative with respect to time has disappeared and has been replaced with a constant, which is the total energy of the system. And this means that the total energy of the system does not vary with time. More explicitly, this still gives us a three-dimensional partial differential equation in spatial coordinates, and this needs to be solved once again with separation of variables. But that is the topic for the next video. Thank you for watching.